Hi, so we have problem number 8, which is non-linear programming problem. And it says, a procurement manager for ABC University is responsible for purchasing the paper used in all the copy machines and laser printers at the main campus. Projected that in the coming year he would need to purchase a total of 24,000 boxes of paper, which will be used at a steady rate throughout the year. Each box of paper consists $35. Estimated that it costs $50 each time an order is placed, and this includes the cost of placing the order plus the related costs in shipping and receiving. The university assigns a cost of 18% to funds allocated to supplies and inventories. Has placing paper orders once a quarter, but he wants to determine if another ordering pattern will be better. He wants to determine the most economic order quantity to use in purchasing the paper. So the question is, can you help the manager to solve the problem? So what is the difference between non-linear programming and linear programming? Non-linear programming can differ from linear programming, where linear programming optimization problems involve objective function and constraints that are linear functions. However, non-linear programming optimization problems cannot be modeled adequately using linear functions of decision variables. You may have objective function that is linear or non-linear, and also you may have constraints that are linear or non-linear. Let's look at some examples that will show objective functions that are linear and also non-linear, and constraints that are linear and non-linear. So if you can look at this, you can see that the objective function is not linear because you can see it is concave, but the constraints are linear because you can see that we have this straight line and also the other straight line, and we have this line here. So we have these endpoints for the constraints, and so we can say they are linear, and this is a feasible region. And in this case, you can see that the optimal solution is at this point where the objective function touches this constraint. This is an example where objective function is linear, but constraints are non-linear. So you can see that the shape of the constraints is convex, and the objective function level curve is linear, and optimal solution is this point, and so our feasible region is this. And here we have objective function that is non-linear because it is concave, and also we have constraints that are non-linear, and here you can see the shape for the constraints is convex. And so the objective function touches the constraints where we can find our optimal solution, and this will be the feasible region. So the objective function and constraints are both non-linear. In this case, objective function is non-linear, but constraints are linear. So you can see that our constraints are straight lines with these endpoints, but the objective function level curves are provided, and then we have the optimal solution at this point. And so this is another example of the objective function, which is nonlinear with constraints that are linear. So actually the differences between linear programming and non-linear programming is that the optimal solution to an linear programming occurs at a corner point. So you can see for linear programming, solution can happen at this corner points. But the optimal solution to non-linear programming might not occur on the boundary of the feasible region at all. And that's why you can see in this case, where we have objective function that is non-linear, with the constraints that are linear, we can see that the optimal solution can happen at this point. And also we have identified that the optimal solution was not at the corner points, but it was found at any point. As you have seen from the beginning, when we are dealing with the linear programming problems, we applied simplex method to identify the corner points of the feasible region. As in this case, you can see we have this corner point 1, 2, 3, 4, and 5, or we could say A, B, C, D, and E. So simplex method could identify the maximum point or the minimum corner point. However, that is different from the nonlinear programming, and therefore for the nonlinear programming we don't use simplex method, but we normally use generalized reduced gradient algorithm to find the optimal solution. So when we are solving nonlinear programming problem, we will not use simplex method, but we'll use GRG algorithm. Let me show you how GRG algorithm works. So we can see here we have the objective function level curves that are linear. We have this curve, and then we have this one, we have the third one, and also we have this one. And our constraints are non-linear because you can see they are convex. So the way GRG works is that algorithm will start anywhere. So it will start from this point A, and then it will move to the direction through the feasible region, the region that causes the objective function value to improve. So the GRG will start from, let's say, point A, and attempt to move to the next and better feasible direction to improve the objective function value. And so it will move from A to B, and then from B it will move to C, and then we can see that we have point D that is better than C, but point E is less than, and so the GRG will terminate at point D. It will terminate at point D because the algorithm will detect that there is no feasible direction that improves significantly the objective function value other than this point D. So the GRG will find that point D is the optimal solution. That solution is known as local optimal solution. However, this might not be the best possible solution. There are two solutions: local optimal solution and also global optimal solution. And I'm going to show you an example that will differentiate between local and global solutions. So let's look at this example. In this case, algorithm can start at point A, point E, and also at point H. And so if algorithm starts, for instance, at point A, it can move to point D, but also it can move to point B. And then it will try to improve the solution, and so it will go to point C, and it won't move to point D because it has to terminate at point C, which is better than point D. Or if it starts from point A, it will move to point D and improve the optimal solution to point C. And so it will terminate at this point, and we call it the local optimal solution. But that is not the best solution, because if the algorithm starts at point E, it can move to point F, and it will also move to point G, where it will improve the objective function value, because it will not move to point H because this is less than point G, and so it will terminate at this point, and this could be the best possible solution as compared to point C. And so we have one local optimal solution at point C, and also we have another one at point G. Point G is also global optimal solution. So if we have seen the nonlinear programming algorithm, which is GRG, can terminate at local optimal solution, that is not global optimal solution to the problem, depends on the starting point, which can be undesirable. So many nonlinear programming problems have single local optimal solution. That is also a global solution. We can say that this is local optimal solution, but also it is a global optimal solution. But when you have more than one local optimal solution, it may not be easy to know whether the local optimal solution is global or not. However, there is a way we can solve this. You can use solver analytic, where the global optimal solution can be obtained by running convexity tester. But we're not going to do that in this class or today. We will address that later. However, today we will look at one of the examples that we can apply the GRG algorithm or nonlinear programming problems. Problem number 8 is one of the examples of the nonlinear programming models, but generally economic order quantity models are actually the most common business problems that use nonlinear optimal models. Today, I will not go deep to explain about the economic order quantity models, but I can just give just a little overview of this. And so, here I have simple example of the inventory management. And you can see that in this case, inventory is ordered on 4-month periods in a period of 1 year. We can say this is one cycle, and we can and in this case we have 12 months, and the inventory is ordered at the quantity of 50. There may be some assumptions to this, that the demand for a product is fairly constant throughout the year. And in this case, you can see that the demand or the annual usage is 150, and the order size is 50. Every time that the order is made is 50. And so another assumption in this case is that each new order is delivered in full when the inventory level reaches 0. So you can see that after receiving 50, then it will be used until when it reaches 0, and then another inventory is ordered. And so in this case, you can see that we have 3 number of orders. We have this one, this, and the last one. So we have 3 number of orders, and the average inventory in this case is 25. So the key issue in this example of the economic order quantity problem is to determine the optimal quantity to order whenever an order is placed. So here is the economic order model, where we have this formula, and this is the total annual cost of stocking a product, which is equal to the actual purchasing cost, DC, plus fixed cost of placing orders, which is D divided by Q times S, plus cost of carrying the product in inventory, or we can say holding cost, which is Q divided by 2 times CI. So D is the annual demand, C is the unit purchase cost of for the item, S is the setup cost, and I is holding cost. Then Q is the order quantity. DC, as I have said, is the cost of purchasing a year's worth of the product. DQ times S, which is the annual ordering cost, where D divided by Q is actually the number of orders placed during the year. And Q divided by 2 is the units held throughout the year on average. And so Q divided by 2 times CI is the annual cost of holding inventory.